Okay, so now I'd like to talk about the cochlea. And the cochlea actually is the inner ear, and it's where stimulus transduction occurs for sound information conversion into neuronal activity. And it's going to happen that this is this sort of spiral shaped kind of cochlear structure right here. This has been 3D printed. It's a bit larger than our own cochlea, but note that it's actually linked up and connected to a series of additional chambers here and a series of what we call these semicircular canals. This entire structure is filled with fluid and is home to what we call hair cells. These are cells that actually have these like stereocilia projections. These are membrane-bound projections that come off the top, and we're going to see they're going to allow for the stimulus transduction, the conversion of not only auditory information in the cochlea, but in this compartment, this portion of this structure, it's called the vestibular aspect of the vestibular cochlear apparatus. We're going to be transducing information about acceleration, linear acceleration, angular acceleration with these semicircular canals, information that's critical sort of for balance and for navigation and for knowing where you are. But the cochlea, this is the inner ear, this component of it here, fluid-filled, the site of location of these cells called hair cells. And I did want to actually show you in terms of the location of these hair cells. Remember, we have the auditory meatus, which is the hole in either side of the skull here, through which the auditory canal is passing, from the pinna, from the outer ear. But I can show it to you here, like on a black bear. This is an Oregon black bear skull that we had the opportunity to actually do a dissection. And this here is the auditory meatus right there. So you can see that hole, right? And what's interesting is that the site of the cochlea, the vestibular cochlear apparatus, is actually in these kind of bubbles of bone right here. These are called the bulla. The auditory bulla is where the cochlea kind of sits. And I've got another skull here that's also from Oregon, a cougar skull. And here, this is a pretty remarkable, skull actually here. And here again is the, auditory canal, right, or the auditory meatus would go right through the auditory canal, go right through there, and the cougar has very prominent auditory bulla, these bubbles, where you would find the cochlea kind of resting. So the cochlea is coiled. And remember, there's going to be the oval window sort of poking in here. From the stapes in the middle ear is going to be poking at that flexible oval window. And remember, this whole structure here is encased pretty firmly in bone. So the sound waves that are going to be, transferred, into the fluid and cause the movement of the fluid, it's going to be in a sealed, kind of bone, the inflexible sort of container. So they're going to work their way sort of down. Let's see if I do this right, down and around and around and around to the tip. And running down the middle of this structure is a membrane called the basilar membrane. And these hair cells sit on that basilar membrane. And the poke of the, the stapes of the sound waves, that was originally related right to the sound that came in, got captured by your pinna, funneled down to the tympanic membrane or auditory, the eardrum, moved the ossicles in the middle ear, poked in at that oval window, and now has generated fluid movements, right? In here, those fluid movements are going to work their way down in this bone-encased cochlea, to the tip here. They're going to then work their way back, right? And then turns out there's another little window there that allows the energy to sort of escape back into the middle ear called the round window, another flexible window. So there's these two little flexible windows, the oval one where the stapes is poking from the middle ear to allow the input, the energy in, and for it to flow all the way around. And then as it works its way back, it can exit out, another flexible window called the round window. And this basilar membrane is fascinating because it varies from the base end. This is the end, where the information is arriving, where the stapes is poking at that oval window, right? And it goes all the way, it'll change in terms of its physical characteristics as it works its way out to what we call the apical end, or the apex. And at the base end, the basilar membrane is very narrow and stiff. So it tends to vibrate in response to high frequency stimulation, and it will move hair cells that are localized, at that base end, at that sort of entry end, to that narrow, stiff basilar membrane. It'll move them much more rapidly. And so it turns out that these, or it'll move them in response to very high frequency sound. So it turns out that these hair cells that are localized towards the base end are going to be critically involved in our response to high frequency sounds. They're going to be essential for our perceptual experience of high pitched sounds. But as the basilar membrane works its way out, right, along, towards the tip here, the apical end, well, it becomes wider and a little floppier, and it'll respond significantly more to sounds of lower frequency. So the hair cells that are actually localized further along that basilar membrane towards the apical end are going to be responsive to lower frequency sounds, and they're going to be essential for our perception of lower pitch, sounds. And there's a homuncular organization of this cochlea, so that the narrow, stiff portion that responds to particularly high frequency sounds is relatively short, and we don't have very good frequency discrimination or pitch discrimination at that upper end. We can hear anywhere from 20 to 20,000 hertz as an infant. Most of us have lost significant high frequency hearing, but we never had particularly good discriminative capacity way up high anyway. Everything sort of sounds like a mosquito up there to some extent. While we have, the wider, floppier as you get further into this, cochlea, that there's much more surface area there that's devoted to very fine discriminations between, let's say, 500 and 5,000 hertz, the lower frequency end, because those kinds of frequency discriminations are important because they relate to the frequencies that are associated with human speech. So the cochlea is a really important structure, and the hair cells are arrayed along that basilar membrane. Now, there is another membrane that's really important here. It's a kind of a gooey membrane, and there's a lot of goo. There's more mucousy goo in your auditory and vestibular systems than you might think. But this gooey membrane overlies the basilar membrane, and it actually is known as the tectorial membrane. And we're going to see that these hair cells, that are arrayed along that basilar membrane, there's going to be one row of them, one sort of row going the whole way from the base end all the way to the apical end at the tip. These are called the inner hair cells, and the tectorial membrane doesn't quite touch their tips, so it allows for fluid to sort of pass over. But then with each one inner hair cell, there are 3 rows of outer hair cells. So here's the inner hair cell, then there's going to be 1, 2, 3, and then as you keep going all the way down that basilar membrane from the base to the apex, and those 3 outer hair cells, so there's 3 times as many pretty much, as these inner hair cells. You're going to have the tectorial membrane sort of stuck. The hairs are going to be stuck in the goo of that tectorial membrane. So we'll talk about the significance of inner versus outer hair cells next.